So you have a chain complex like this. So these are our groups C0, C1, C2, C3, C4 in homology. This is chain complex. And then you have your maps here. From this chain complex, you get a cochain complex. A cochain complex consists of functions which act on these simplices. So these singular simplices, functions will act on them, and that is precisely what a cochain complex is. So say you have some function f0 acting here. So f0 acts on v0. So f0 lies in this cochain complex. Similarly, say that you have two functions here, f1 and g1. f1 acts on v0, v1, g1 acts on v0, v1, or g1 and f1 have domain as v0, v1, this entire edge. So they lie in c1 right here. Similarly, say you have a function f2 which acts on v0, v1, v2. It lies in c2. Similarly, you could have function f3 acting on v0, v1, v2, v3, lies in this cochain complex right here. And you have f4 which acts on this simplex here, and it lies here in c4. So these are all simplices, but they're denoted by vertices, as we have seen in homology multiple times. So the idea of cup product is this. So say you have these two functions, f1 and g1, they act on two vertices. You want to make sure that they act on three vertices. So how do you do that? You make f1 act on these two vertices. So f1 acts right here, and then g1, this acts on these two vertices. Again, f1 and g1 are just acting on two vertices the way it was defined, but now you can glue them around v1 and you can make them act on three vertices. So this action on three vertices means that now it will lie in this c2 part. So this f1 cup g1 lies in c2 because it acts on three vertices. Similarly here, so say you have f2. So say f2 acts on these three vertices. And then you have f1 which acts on two vertices. You make f1 act on two vertices. So again, f2 is just acting on three vertices, 1, 2, 3, and f1 on two vertices, but you can glue them around this vertex v1, have a common domain, and that will ensure this combination of f1 and f2 will lie in c3. So this combination is cup product. Similarly here, now here what you can do is you can probably take three vertices and then three vertices. So these three vertices will come from somewhere here. So you can have, f2 which acts on three vertices, and another g2 which acts on three vertices. So you have f2 here, g2 here. So f2 coupled with g2 lies in c4. Or you can take f3 which lies or acts on four vertices. So say f3 is acting on these vertices right here, and coupled with something acting on two vertices, say f1. So again, the common vertex is there, v3. So f3 coupled with f1 lies in the c4. So this is something like polynomials. So you just have constants here, because in c4 you could also have just a function f4 which will act on all four vertices, and you glue on v0 acting f0 here. So you can have 0 and f4. So constants are here in c0. You have, say, x here, and then you have x square here. So just like you cup f1 and g1, they act like x. So, and this cup product acts like multiplication. So x1 times x1 gives x square. Similarly, you have x cube here. You think of this f1 as x, and then you cup it with f2 which is like x square, so you get x cube. So again, f1 x, you can see the correspondence, x square f2, cup these two is same as multiplying these two. So f1 cup f2 multiplication here. Similarly, you get x4 here, which could be x3 times x, which is same as f3 coupled with f1, and you have x cube and f3. So you can see the correspondence clearly. So the idea is that we want to have polynomial rings which are associated with surfaces, and we are going to compute a large number of these rings in examples later on. Now the only thing we have is we have these maps D. Now this D also has to act on cup product, so we have to give a precise definition for this D. So let us now move more formally. So say you have, say this var phi is in Ck and this phi is in Cj. The cup product lies in Ck plus j. This we have just seen above, and this is precisely defined like this. So the first element acts on k vertices, the second element acts on k2 k plus j vertices. Notice that there is a common vertex here, vk and vk, and sigma is for singular complexes. Now this should lead to cohomology groups. Now the reason why we are going from here to cohomology is simple. The purpose of algebraic topology is to lead us from topological spaces to groups, and this is the primary reason why cohomology is much more powerful than homology, because you have this cup product. So you have this cup product which did not exist in homology. It's precisely because you can glue these functions to act on higher simplices. So this kind of gluing you could not do in homology, because we have functions here, you can glue their domains to get a cup product. Now you have to go from here to here. So what are this cohomology groups? So these cohomology groups by definition nothing but co-cycle over co-boundary. So this hk is this part, say this hj is this part, and hk plus j is this part. Each one of them is co-cycle over co-boundary, co-cycle over co-boundary, co-cycle over co-boundary. So basically co-boundary acts as 0 because you modulo it out. So if you start with a co-cycle, you multiply it with a co-cycle or take a cup product with co-cycle, you should get a co-cycle, because co-cycles are precisely what is going to give the cohomology groups, because co-boundary is just going to be 0, you modulo out co-boundary. So co-cycle, you cup with co-cycle, you should get a co-cycle. On the other hand, if you cup a co-cycle with a co-boundary is 0, it's a polynomial multiplication. So say you x multiply with 0, you should get a 0. So if you take a co-cycle here and a co-boundary here, you should get a 0. 0 means co-boundary here. So co-cycle with a co-boundary should give you a co-boundary. Similarly, if you take something x here and 0 here, you should get a 0 here. That is, if you get a co-cycle here, take a co-cycle here, but take a co-boundary here, then you end up with a co-boundary here because you need to get a 0, and that's it. So these three conditions have to be satisfied by our this operator d, this differential d. And we will prove this lemma that this d of acting on the cup product of these two is just given by this formula. D of this var phi cup with phi is d of var phi cup phi minus 1 to the power of k var phi cup t phi. I've written 3 times because we have to verify these 3 conditions. So what does co-cycle mean? You know the co-cycle means it is the kernel of the map. So d of a co-cycle is 0. So because basically cohomology is kernel over image. So this is kernel. If you apply further d to it, is going to go to 0. So basically if you are 0 here and you are 0 here, you'll be 0 here. So the first thing you notice is you start with this var phi and phi. So var phi is a co-cycle and phi is a co-cycle. So that means this is 0 and this is also 0. So this entire thing cup product is also 0. So this term will be 0. You do a cup with 0, you get 0. Here also second term you get a 0 because this term is 0, this term is 0, entire thing is 0. So if d of something is 0, that means this lies in the kernel. So that means this is itself a co-cycle. So the first thing is done. So this is 0, therefore this is a co-cycle. So this is done. Now coming to the second part. So So again, recall that co-cycle of something means d of is 0, and co-boundary means that this thing is d of something, because co-boundary is always image, and this image is coming from d, so image of something. So now co-cycle times co-boundary, that is d of this var phi is 0. So this is 0, that means this entire term is 0. But then you have this coupled with a co-boundary, because co-boundary is always d of something, is d of something. So you get a co-boundary. Similarly here, your second part is co-cycle, this is 0. So this entire term goes to 0. And you get this is equal to co-boundary of something. And that is the end of the story. Now we just prove the lemma. So this is what we have to prove. And this sigma is just a singular map, so we will focus term by term. So this term is right here, and the second term is right here. So that's it. By definition, when you apply this to it, you first d phi times this. So just apply the definition of the cup product. So this you have done, but this is nothing but phi times delta. So when delta acts on, so this term you just copy as such right here. This is just copied as such right here. Nothing has changed. And on the first part, you have to apply d to the first part. And you apply d to the first part, you apply this partial here. And that's what you have done. Similarly, for the second part, this partial has to be applied to the phi part. So first, definition of cup product. This minus 1 to the power of k, don't think about it, just put it directly. Now you have the cup product definition. Now you apply d. First part you keep as such. So this part you don't touch it, just copy it down as such. For the second part you put this partial. So that's what we have done for the second part. So we have this. So again, this ith vertex is missing, ith vertex is missing. Now we just add them up, and you will see this is just application of partial to sigma. So you will go all the way from 0 to k plus j plus 1, and that's precisely what the cup product would be. And this partial of sigma would nothing but is, by definition, this is equal to d of. Now the only thing we have to see here is that this ends at k plus 1 and this ends at k. So ends at k plus 1 means that you have this term 0, 1, 2 all the way to k plus 1, and then you have, obviously you have a k here also, k plus 1, but here you start with k plus 1 and so on. So the only thing you need to notice is that the kth term here in this expression will cancel out with k plus 1th term here. So this will cancel out right here, and that you can just see by simple expansion. You will have this first term here. So let us focus on this expression which I have just copied from here. For the k plus 1 term, you will have k plus 1 right here, but k plus 1 means the k plus 1 vertex is missing. So your last vertex would be just k, and all other vertices would be there all the way to k. From this expression, your kth term would be starting with k right here, and by definition you have all the vertices still k. So you have all the vertices still k, but here the kth vertex would be missing. So this vertex is missing because your hat will come to the first vertex. So you will start from k plus 1. So now you can see both of them are exactly the same. This term, so this term, it comes from this, and the top form comes from this.